The last algorithm we're going to take a look at to clean up or remove zeros is what we call the converging pointers algorithm. So we're still going to scan from left to right like we did before. The difference now is that we're going to track the last item in the list, along with just going from left to right. So now, whenever we find a zero, we're going to copy the last item of our list in place of the zero. So we're going to take the last item and put it wherever that zero is. It could be at the beginning, it could be at the middle, doesn't matter. We're just going to take the last item in the list and copy it there. And then we're going to move that pointer or that arrow that we're going to have at that last item and move it to the next to last item, and then we're going to repeat. So we're going to keep checking to see if we find a zero, and when we do, we're going to copy the next to last item and store it in place of the zero, and we just keep repeating this until we get to the end of the list. Let's use the same example as before with our 10 values. So we have an arrow pointing at the first item in the list, and then now notice that we have this second arrow that points to the very end of the list. So this is the value that we're going to use to copy to a zero whenever we encounter it. So notice that our first value was a zero. So that means we took 27 and we copied it in place of that zero. So that's why 27 is now the first item in the list. And then notice that over at the right side, we move the arrow over one place. Because as we said before, we're going to move to the next to last item, and now we're going to repeat this whole thing again and try to find the next zero and copy whatever value is over here on the right side. So now we look at the second item in the list. It's 24, it's not zero, so we're not going to do any copying, and we're just going to move on to the next item. We get a 16 here. Once again, it's not zero, so we don't do any copying. We see here that we get a zero, so that means we need to copy whatever is in the right pointer and copy it into the left pointer. Now notice that when we do that, we copied a zero, so it's still zero, but that's okay. That's not a problem. We'll eventually fix this, because notice that the right pointer is now moving over to the next to last item, which would now be 21. So the way we fix it is, okay, well, let's just take the 21 and copy it to the zero. So we kind of got rid of two zeros at one go. So we copy 21 here, and then we move our right pointer to the next item, which would be 23. And we can just keep repeating this if we want to. We can move the left arrow over to 36, 42, and so forth, but we would see that we would no longer have zeros. Yes, I know there is a zero all the way over here, but just like what we did before, we're going to stop whenever the position of left or the value of left is greater than the value of legit. So here we would stop when we get to the 8th item in our list, because then we know we've gone through all of the legitimate values in our list. So here is the complete algorithm here. So we still need to get the values of n, the list of items, legit, and then left. So all those are the same as before. We now have a value called right, and we're going to initialize it to n. So that's going to be our right pointer that we're going to use for copying stuff over to our zero values. So as long as left is less than right, so in this case, instead of stopping whenever we get to it where the value of left is greater than legit, we're just going to say we'll stop when left is equal to right, because we know that the values in the right side are no longer legit. So we'll do steps 6 through 10. So here we'll say that the item at position left is not zero. Then we're just going to move the left arrow over by one spot. If the item at position left is zero, then what we're going to do is we're going to reduce legit by 1. We're going to take the value at position right, copy it into the value of position left. We're going to reduce right by 1. That allows us to move that right arrow over to the left by one spot. And so we'll just keep repeating that. And then eventually, if the item at position left is 0, then we'll also reduce the value of legit by 1. So we have this last step here in case we get to like the part where both our left and right arrows are at the same spot, and that spot happens to be 0, because in that case we don't have any values to copy into that 0. So we'll just reduce legit by 1, and that way we don't have to worry about that 0. Let's analyze this algorithm. So we'll do the time first, and just like we did before, and I'm going to ask you, what is the worst case scenario? Pause the video if you need to, and then resume once you think you know the answer. The worst case scenario here is that all items are 0. What that means is we're going to repeatedly copy the element at position right into the first position. And each time we copy, we're going to reduce the value of right. So we're going to keep moving from right all the way to left. So we're going to do n copies because there are n items in the list. So since this happens n times, it's going to take theta of n time. Now what about the space? Well, we have the original list, which is going to be our input, and then we need just a couple of variables, n, left, right, legit. So what this means is just like our shuffle left algorithm, this is going to be a pretty space efficient algorithm because we just need a couple memory locations on top of our input. So the whole point here is this is the same asymptotic notation as the copy over algorithm. That was also theta of n time. But we don't use any additional list with this algorithm. So if we had to pick which of these three algorithms that we just talked about would be the best for this problem, this algorithm right here would be our best choice because we have the asymptotic time of our first algorithm, it's theta of n, and we don't need any major additional space in order to make it work.